Which of the following is the primary goal of CO2 flushing during the ECMO circuit priming process? A. To check for leaks in the oxygenator. B. To displace nitrogen and facilitate the dissolution of any remaining microbubbles. C. To acidify the prime to match patient pH. D. To sterilize the internal surfaces of the tubing. Answer: B. To displace nitrogen and facilitate the dissolution of any remaining microbubbles. Explanation: Carbon dioxide is significantly more soluble in crystalloid/blood than nitrogen or atmospheric air. By flushing the circuit with CO2 first, any small bubbles left behind after priming will dissolve rapidly into the fluid, reducing the risk of air embolism. When priming an ECMO circuit for an emergency neonatal case, which fluid is most appropriate to ensure hemodynamic stability and osmotic pressure? A. Normal saline, 0.9% NaCl. B. Plasmolite alone. C. Balanced salt solution supplemented with 5% albumin or packed red blood cells, PBSEs. D. Sterile water. Answer: C. Balanced salt solution supplemented with 5% albumin or packed red blood cells, PBSEs. Explanation: Neonates have a small native blood volume. Priming with just crystalloid would cause massive hemodilution. Adding albumin or PBSEs maintains oncotic pressure and hematocrit during the transition. During the priming of a centrifugal pump, what is the most critical step to prevent pump depriming? A. Keeping the RPMs at 0 until the patient is connected. B. Ensuring all air is removed from the cone or impeller housing. C. Gravity filling the circuit from the venous side only. D. Pre-coating the circuit with heparin. Answer: B. Ensuring all air is removed from the cone or impeller housing. Explanation: If an air bubble is trapped in the center of the impeller, the low-pressure zone, the pump will lose its prime and fail to move fluid, even if the motor is spinning. The formula used to estimate the required ECMO flow rate, Q, for a pediatric patient is often based on the cardiac index. What is the standard target flow for a pediatric patient? A. 1.0 to 1.5 L/min/m2. B. 2.0 2.4 liters per minute per square meter. C. 3.0 3.5 liters per minute per square meter. D. 5.0 6.0 liters per minute per square meter. Answer: C. 3.0 3.5 liters per minute per square meter. Explanation: Pediatric and neonatal ECMO typically require higher flows per square meter of body surface area, BSA, compared to adults to meet higher metabolic demands. In veno-arterial, VA. ECMO: If the pump flow is 4.0 liters per minute and the patient's intrinsic cardiac output is 2.0 liters per minute, what is the total systemic blood flow? A. 2.0 liters per minute. B. 4.0 liters per minute. C. 6.0 liters per minute. D. 8.0 liters per minute. Answer: C. 6.0 liters per minute. Explanation: In VA ECMO, the circuit flow and the heart's residual output work in parallel. The total systemic flow is the sum of both, ECMO plus native. Which physical principle explains why increasing the length of the ECMO cannula or decreasing its diameter significantly increases the resistance to flow? A. Bernoulli's principle. B. Poiseuille's law. C. Archimedes' principle. D. Fick's law. Answer: B. Poiseuille's law. Explanation: Poiseuille's law states that resistance, R, is proportional to the length of the tube, L, and inversely proportional to the fourth power of the radius, R4. Small changes in cannula diameter have a massive impact on flow capacity. Chattering or kicking of the venous line is a sign of what physiological state? A. Excessive pump speed, RPM, relative to venous return. B. The oxygenator is clotted. C. The sweep gas flow is too high. D. Hypertension in the patient. Answer: A. Excessive pump speed, RPM, relative to venous return. Explanation: If the pump is pulling more blood than the venous system is providing, the vessel wall can collapse against the cannula tip, temporarily stopping flow until pressure builds back up. This cycle causes the line to shake/chatter. To calculate the oxygen delivery, due to, on ECMO, which of the following variables is not required? A. Hemoglobin concentration. B. Arterial oxygen saturation, SA2. C. Pump flow rate, Q. D. Sweep gas flow rate. Answer: D. Sweep gas flow rate. Explanation: due to is a measure of how much oxygen is being delivered to the tissues per minute. It depends on blood flow and oxygen content, not the rate of sweep gas, which primarily manages CO2 removal. In VV-ECMO, recirculation occurs when oxygenated blood from the return cannula is pulled directly back into the drainage cannula. How does this affect the calculated ECMO efficiency? A. It increases the patient's systemic SA2. B. It increases the premembrane saturation, SpO2, and decreases effective patient oxygenation. C. It has no effect on oxygenation. D. It causes the pump to spin faster at the same RPM. Answer: B. It increases the premembrane saturation, SpO2, and decreases effective patient oxygenation. Explanation: recirculation creates a short circuit where the ECMO machine is reoxygenating already oxygenated blood, leaving the patient's actual systemic circulation hypoxic despite high saturations in the circuit. If the pressure drop across the oxygenator, delta P, begins to rise steadily over several hours, what is the most likely cause? A. The patient is waking up. B. The sweep gas is disconnected. C. Thrombus, clot formation within the oxygenator fibers. D. The venous cannula has migrated. Answer: C. Thrombus, clot formation within the oxygenator fibers. Explanation: delta P, premembrane pressure minus postmembrane pressure, measures the resistance within the oxygenator. An increase indicates that the pathways between the fibers are becoming obstructed, usually by fibrin or clot.